Right, good morning, everybody. Can you hear me? Can you see my screen share at the moment?
Good morning, sir. It's
Okay, right. Okay, let's take a few seconds to scan your attendance, and then we shall begin and continue with where we left off last week. Okay, we shall begin with our class today. All right. Once again, good morning, everybody. How's everyone doing? So firstly, let me just apologize for what happened last class. I was having a bad headache from the morning and right until the class time. I thought like I was going to recover before the class time and conduct the class as usual, but apparently until like before class, 1 hour before class, I wasn't still doing very well. So I thought that instead of conducting the class while I was like distracted with that, I might as well conduct the class another time when I'm in a better state, right? So I deeply apologize for that. That wasn't expected. So thank you for very much for those who who gave me a care message. So I really appreciate it. So I'm a human after all, right? Just like you are. Okay, so let's just continue from where we left off, right? Actually, we are only a little bit left to end this chapter. So I wanted to finish this chapter so much in the last class, but I just couldn't do it in the last class, right? So let's take a look at where we are currently at. All right, so if you remember, we are in chapter number 7, and chapter number 7, we talk about sequential logic. The sequential logic, how is it different from combinational logic? Remember, in sequential logic, we have memory. So that is the main difference. We have memory. We have in sequential logic, we remember what is the previous state or the previous input that is given. So in combinational logic, we don't care about what the previous input is, what the previous outputs are. But in sequential logic, we care about them. We care about what is given to the circuit now and what is given to the circuit previously. So that is what makes sequential logic different than combinational logic. All right. In sequential logic, also we've learned a couple of things. Let me just go through to this one. Okay. So these are the two key things that we learn in sequential logic. We learn about latches and we learn about flip-flops. So latches and flip-flops, they are the building block. They are the foundational building block that is being used nowadays to construct memory. So if you look in your phone, if you look in your laptop, in any pretty much any electronic device, they have memory. So this memory is what allows the phone or laptop to be useful, right? So without memory, pretty much your laptop will be useful. So imagine that if you turn on your laptop and then you turn on the browser and then you visit google.com and then the next time you turn on the browser, you have to reinstall the browser again because it doesn't have memory. It doesn't keep what you install on the phone next time, right? So it would be a pretty useless device without this memory. So memory is one essential component in any um, electronic device, and memories are constructed using this building blocks known as latches or flip-flops. Right, so we talk about what are latches, how they function, and what are the few types of latches. So let's just go through. Right. So we talk about latches. So there are a few types of latches that we talk about in class, and I remember we talk about SR latch. Remember SR latch, and we talk about D latch in the class. And as a homework as well, I think I did give you homework on to do research on the remaining two latch, that is the JK latch and as well as the T latch. So these are the four latches that we learned in the class: SR latch, D latch, JK latch, and T latch. And similarly for flip-flops also, you also have the same variation. You have firstly SR flip-flop, and you have D flip-flop, and you will also have JK flip-flop, and you will also have T flip-flop. So in the last class, I remember that we already covered SR flip-flop and D flip-flop, correct? So in today's class, we are going to cover the remaining two flip-flop, and then we will end this class and we will end this chapter. Actually, there's not much left. I think we will finish this, we'll end this class before 9 a.m. actually. Yeah, so let's just go through a refresher on what was done in the last class. So flip-flops, go through very quickly. So what is the difference between a flip-flop and a latch is the trigger signal. Okay, so it clocks. So flip-flop functions on clocks instead of enables. So clock is this square wave signal. Usually clocks comes in square wave signal. So in a clock, you have several components: positive edge, negative edge, high and low. So positive edge is the vertical line going up, negative edge is the vertical line coming down over here, and you have also low, which is a horizontal low level, and high over here, which is horizontal high. All right, and a flip-flop only functions when you have a trigger. So what happens if you have a trigger? So a flip-flop can function in either a positive trigger or a negative trigger, right? So a positive level trigger, it means the flip-flop will only function at this positive edge, rising edge, and a negative or a negative or a negatively triggered is when the flip-flop functions at this negative edge over here. Okay. So the main difference over here is that latches and flip-flops, they function on latches function on level, so which means it will function only when the level is like high over here, and flip-flops functions only when you have a trigger at the edge, it's the vertical line. All right, so I believe we went through some kind of timing diagram. So this is the timing diagram that I went through you guys in the class. What is the difference between the D latch and the D flip-flop? How is it different? So if you have not understood yet, I highly encourage you guys go back and watch the recording on where I explain this timing diagram. Okay, so the key point is that D latch functions when the enables are high over here. So only when the enables are high, the output can change state. So in D flip-flop, it's different because the output can only change state only when you have this vertical rising edge over here, and over here. Okay, so it functions like at the vertical edge. D latch function at the horizontal level. So we went through that was D flip-flop, and then we also went through SR flip-flop. The SR flip-flop, the circuit looks like this, and we also went through this truth table, and we also went through characteristic table, what is the difference, and also we went through this timing diagram. Okay, and we also I think we didn't go through this one in the class, but this one I left as an exercise to you guys to determine the output when you're given this waveform. And it's assumed that initially it's reset. So hopefully you guys done this exercise also at home. And today we are going to continue from where we left off, right? So we went through D flip-flop as well. Right. So what's left is actually just very simple. It's just JK flip-flop and T flip-flop. All right. So JK flip-flop is very similar to JK latch. So if you've been through JK latch, this will come in very familiar to you guys. All right. So in JK flip-flop, the operation is very similar to the SR flip-flop, but it has got no invalid state. If you remember in SR flip-flop, all right, there is a weakness with SR flip-flop, and the weakness is that when both of the inputs are 1. Okay, let's take a look at this one. Okay, So this is the weakness of SR flip-flop. So it's when S and R, these two inputs are 1, this puts the flip-flop in a invalid state. Okay, so the output is indeterminate. There is no fixed output. The output can bounce from 1 to 0 in a very you cannot determine for sure. Is it a 1 or is it a 0, or is it's bouncing from one another? So okay, so this is the drawback of a SR flip-flop. So in a JK flip-flop, what it is different is that JK flip-flop, we overcome that. We overcome this weakness in JK flip-flop. Okay, right. So the difference is that so JK flip-flop, the diagram looks like this. It's J and K. Instead of SR, we modified this letter to be J and K. However, in the JK flip-flop, the truth table looks like this. So how is it different? So let's take a look here. So in JK flip-flop, everything else is the same with SR flip-flop except for the last line. Okay, so let's take a look. So if the two inputs J and K 0, 0, that puts your JK flip-flop in a no change state. So which means if you have 0, 0, and then you have okay, so this is a clock. This clock X, it means that there is no trigger. So if there is no trigger and this one is 0, 0, then your output will not, your flip-flop will not function. So the Q will just remain as Q. Okay, so that is one example. So what if you have 0? Let me just add one more row here. If you have 0, 0, and you have a positive trigger here, positive edge over here. So you have 0, 0, you have positive edge. So 0, 0 for JK flip-flop, it puts it in a no change mode. So if you are a no change mode and you have a positive edge, your output will still be here because your flip-flop is in a no change state. Okay, no change mode. All right, so let's take a look at what happens if you have 0, 1. If your flip-flop input is 0, 1, and then you have a trigger, a positive edge trigger, so what happens? So if you have 0, 1 like this, you can imagine that this is the S and R. So it's similar to S and R. So if you have 1 over here, it is putting your flip-flop into a reset state. So reset state means that your output, you will want to make the output to be 0. Okay? Similarly, if you have a set state over here, you have a trigger over here, and your output goes to 1. Okay, regardless of the past input, regardless of past output. Okay, if you put it, if you give it a 0, 1 to this JK flip-flop, the output here becomes 0. It becomes if you give 1, 0 over here to the JK flip-flop, the output here will be 1. Okay, that is provided you have a trigger over here. Okay? If you don't have trigger, so no matter what you give to the input, the flip-flop will not function. All right, so let's take a look at the last line over here. So this last line was where we had trouble with the SR flip-flop. Remember? So with SR flip-flop, if you give 2 1s over here and you give it a positive edge trigger, the SR flip-flop goes into error. So into an indeterminate state. So the output cannot be determined. But for JK flip-flop, what happens is that if you give it 2 1s over here, this JK flip-flop goes into a state we call a toggle state. Okay, so toggle state means that it will, the output will be flipped. The output will be the inverse of what it previously had. Okay, so for example, if the output, previous output was 0, it's going to make it a 1. If previous output is 1, it's going to make it a 0. That is what it means by toggle. So that is why in this table, we write this as Q bar. Okay, so if you give 2 1s over here, and then you have a trigger, the output will be the inverse of Q. Okay, so we take the current output and we reverse it. That is what it means by toggle. Okay, so this is what I was talking about. All right, so let's just go through a characteristic table so that you guys can understand and see much more clearly on how this JK flip-flop is different. So in this characteristic table, we are going to assume that we have a trigger. Okay? We are going to assume that for every row in this table, we have a clock trigger. Right, so let's take a look at the first row. So in the first row, we are giving the input J and K to be 0. So you can imagine that this is a flip-flop, and this is J, this is K. Okay, all right, this is Q, and this is Q bar, like that. And we can connect this to a block. All right, so this is the input that you are giving to this JK flip-flop, and this is the output that you want to know. All right, so if you give a value of, so let's assume that 0, 0, we give a value of 0, 0. Okay, we gotta have, for any flip-flop, we gotta have the initial output. So we are going to assume the initial output is 0, like that. Okay, let me just change this pen color so that it's gonna be clear. Okay, so we are going to assume that the initial output is 0. Okay, so what happens if you give a 0, 0 to the J and K over here? So we give a 0, 0. So if you give a value of 0, 0 like this, what happens is that this puts your flip-flop into a no change mode. Okay, so no change mode. So what happens is that in a no change mode, it's going to take whatever that is already at the output and it's going to keep it that way. Okay, so that's why in the present output, I put a 0. This is what we currently have at the output, and what will happen next is that it will stay at 0 because your flip-flop is in a no change mode. Okay, all right. So what happens if you have if you give 0, 0 and your current output is 1 like this? So this is also to mean we give 0, 0, but your existing output over here is 1. Okay, so 0, 0, and this one is also in a no change mode. Yeah, just write it as like this, and your existing output is 1 like that, right? And you have, so the question is, what is the next output? So what will happen if you put in like this 0, 0, and then your current output is 1? So that means what will happen is that your flip-flop will be in no change mode. So no change mode means whatever output that you have currently, it will preserve it. Okay, it will stay the same. So that means that your next output will just stay at 1 because this is what you have at the present time. Okay, so that is 0, 0. Okay, so what if you have 0, 1 like this? Okay, so we are going to change this over here, 0, 1, and then your existing output is, let's say your existing output is 0. Okay, and okay, say your existing output is 0, and then all of a sudden you want to change this input. You want to put in here 0, 1. So question, what will happen at the output? So 0, 1 puts it in a reset mode. Reset mode, right? So these two are reset mode because you put in a 0, 1 over here. 0, 1 puts your flip-flop into a reset mode. So in a reset mode, what is going to happen is that it does not care whatever that you have at the current time. What it's going to do is just going to make it a 0 no matter what. Okay, if you have 0 at the current output, you make it 0 then as the next one. If you have 1 over here, you make it also a 0. So bottom line, if you have 0, 1 like this, it does not consider anything. It will just make your output to be 0. Okay, so that's why over here, if you have 0, it becomes 0. If you have 1, it also becomes a 0. Okay, because your flip-flop is in a reset state or in a reset mode. So the opposite happens if you have over here 1, 0 like this. So this puts your flip-flop into a set mode. Okay, 1, 0 puts you into a set mode, and in set mode, what happens? Set mode, you want your flip-flop makes your output to be 1, right? So if you give you 1, 0 over here, your existing output is 1, it's going to make it into a 1. If your existing output is 0, it's going to make it into a 1. So no matter what happens, your flip-flop will make it your output to be 1 if you give this value. Okay, so this is also a set mode. All right, so let's take a look at the last one. Sorry, this one is not this 2 line, but this 2 line. Right. So Let's take a look at this last two lines. This is where it is different from the SR flip-flop, okay? So what happens if you have two of this to be ones? Okay, if you give, if let's say you have current output is 0, and then you put two ones over here. So what happens to this output 0? So this output 0 will become a 1, okay? Because why? Because you put 1 into a JK flip-flop, this makes your flip-flop into a toggle mode. Okay, toggle mode, and toggle mode says that whatever output is just going to flip that output. Okay, so if your current output is 0, it's going to flip it into a 1. Okay, so similarly, if your current output is 1, it's going to flip it into a 0. So say for example, if you have a 1 over here, and then you supply a value of 1 over here, what will happen is this 1 will instantly change to 0, like that. Okay, it's going to flip that value. If it's 0, it's going to turn into a 1. If it's 1, it's going to turn into a 0. So that is how this toggle mode works. Okay, so hopefully that makes sense to you guys. All right, so let's take a look at this timing diagram. So this timing diagram is an important one, so pay close attention to what I'm gonna present over here. So suppose we have a JK flip-flop. Okay, no problem with this, and this diagram is given to you. And okay, what's different with this diagram? So let's take a look at this diagram. The difference between this flip-flop and the other flip-flop is this bubble over here. Okay, so this bubble over here indicates that this is a negatively triggered flip-flop. Okay, which means negative trigger. Okay, which means this flip-flop will only be triggered at the falling edge of the clock. Okay, falling edge. Okay, so if you look at the clock over here, so the falling edge are at this point over here, falling edge, falling edge, falling edge. Okay, so let's just take a look at this timing diagram, what is going to happen. So initially, we assume that the flip-flop is the output of the flip-flop is 0, like that. Okay, and this is the initial state. All right, so the clock just repeating square wave signal like this. And now we are going to monitor the behavior of this flip-flop when we change the input. Okay, so let's just go through this timing diagram from left to right. So that is how we progress through the timing diagram. Okay, so this is in the time axis. Okay, over here in the beginning we have 0 seconds, and then we progress 1 second, 2 seconds, and so on. Okay, so let's start with on the most left, and in the beginning what we have is 0 at the output. And what happens? So you have a clock signal, and then you have JK to be 1 and JK to be 1 over here. So this puts your flip-flop into a toggle mode. Okay, toggle mode. But does the output change the moment you give the flip-flop 1 1? The output does not change until it reaches the trigger point. So the trigger point is when you have this negative trigger, okay? Because there is a bubble over here, remember? So when you have this trigger, then the flip-flop will react to what you have at the input. So at this specific moment, it's going to take this value, it's going to take this value, and it's going to figure out, oh, okay, 1 1. Then this means that it's in a toggle mode. So the flip-flop is just going to take whatever value over here, and it's going to toggle this to another value. Okay, that is how we get the value high over here. And then after this brief moment that it toggles, it's just going to stay there. It's just going to stay there until it gets the next trigger. Okay, so it's just going to stay here. So look at this. Everything here stays the same. Okay, until you meet the next trigger at this point. So until you meet this trigger. So at this point of trigger, it's going to take this, and it's going to take this value. It's going to read what's the input at this trigger point and determine the output. So at this point when it's triggered, the J is 0, K is 0. So what state is it in? 0 0 is in a no change state. So no change state means it's going to take whatever is existing at the output, it's just going to keep it that way. So at this moment, at this point, whatever is at the output is 1, so it's just going to keep it a 1, so you don't see any changes. All right. So what I want you to notice over here, that in this duration, okay, in this duration, there is no trigger whatsoever, right? There is no trigger. So even though you change this, your output doesn't react to that. Your output does not change, because at this point when you change this trigger, at this point when you change the input J and K, the flip-flop does not get the trigger signal. Okay, the trigger signal only happens like at the end over here, at this falling edge. All right. So, and okay, let's progress to the timing diagram further. So we see that after we have this trigger at this point, so this output is just going to stay this way. It's just going to keep this output no matter what you do. Okay, even though you have this change over here, this output is not going to change, because it is only changing when you have this another trigger over here, which is this vertical line over here. So at this vertical line, it gets the trigger. Now it's going to read what is the input at J and what is the input at K. The input at J and K, J is 0 and K is 1. So J0, K1, that puts your flip-flop into a reset state, right? Reset state. So in a reset state, what is going to happen? In reset state, your output is going to go to 0 no matter what. Okay, output is going to go to 0 no matter what. So over here, the output is 1, so it's going to make it into a 0 over here. Okay, so that is why we have this reset state. Okay, right. So reset state, and then it's going to keep this output 0 until it meets the next trigger over here. So in this next trigger, it's going to read this. It's going to read this. So what state is it in? J is 1 and K is 0. So this is in a set state. So what happens in a set state is that the output will be 1 no matter what. So the flip-flop will make the output to be 1 regardless of what you have at the input, regardless of what you have at the output of the previous time, right? So over here we have 0. The existing output is 0, and it's going to make it into a 1. And then it's going to keep it that way until it meets the next trigger. So the next trigger is at this point, and it's going to read this again. So this is also again in a set state. The set state is going to make the output 1. So the existing output is 1, is going to make it into a 1. So 1 becomes a 1, so you don't see any difference at the output. Okay, so that is how we interpret this timing diagram. And at this point, I really hope that you guys can also produce this timing diagram again. That is how you guys can learn even more. Okay, so I can be explaining this timing diagram like 10 times to you for 2-3 hours, and you're still not going to get it, because you are only going to understand if you can make this yourself. Okay, so I believe in one thing. You don't really understand. I believe in this principle, right? If you don't really understand something until you can build it. So build things. In this course, I encourage you to build things. That's why I encourage you guys to experiment with all this online software that's free, because you can use them to build and you can use them to test your understanding. All right, so that is JK flip-flop. The same can be done for the last flip-flop. Okay, so the last flip-flop is the T flip-flop. So T flip-flop is short for toggle. Okay, T stands for toggle, and this T flip-flop is actually internally it's still a JK flip-flop, but what is different is that they connected this J over here and K over here to one single input, and they call the input a T flip-flop. Okay, you can imagine that this whatever is this red box is a JK flip-flop inside here. So that J and K it's connected to a common input, which is a T. Okay, so what happens is that it can only have 2 possibilities over here because it's connected in that way. So T can either be 0 or 1. So if it's 0, then what goes into here is 0, 0. So which means it's going to be a no change state. So when you put T equals to 0, it's going to get your flip-flop is going to get a no change state. if you put your T to 1, it's going to be in a toggle state. Okay, because you put T 1 and inside here you get 1, and inside here you get 1 over here. So it's like JK flip-flop, you get 1, 1, and that means it's in a toggle state. Only two possibilities, no change or toggle. Instead of a JK flip-flop, you have 4 different, right? You have 0, 0, 0, 1, 1, 0, and 1, 1. So in the toggle T flip-flop, you only have no change and toggle. Right, so same thing, this is the block diagram, and this is the clock, and right, and sometimes you can also draw it in this way. TFF stands for T flip-flop. All right, so I believe this is right now very understandable. So assuming that the clock is triggered, so this is the characteristic table, right? So if T is 0 and your current output is 0, so which means what's going to happen next is that your next output is going to be 0. Okay, because this T flip-flop is in a no change state. No change mode, 0. Second one also, no change mode, 0, because your T is at the value of 0. Okay, so your current output is 1, and it's going to preserve it because there's no change mode. 1 stays 1. And what happens if you have a toggle, T to be 1 over here? This puts it into a toggle mode. Okay, both of these rows, they are in a toggle mode. So if your existing output is 0, it's going to toggle it into a 1. If your existing output is 1, it's going to toggle it to 0. So that is the difference. All right, so that will be the end of our flip-flop. So 4 flip-flops in total: SR flip-flop, D flip-flop, you have JK flip-flop, and you have a T flip-flop. All right, so I hope that by now you understand how the flip-flop, how all this flip-flop works. So basically, so these are all the block diagram. So these are just a summary. So holds on. So these are the very basic difference. So in the SR flip-flop, so it's a basic data storage device which holds until reset occurs. Okay, so and you have D flip-flop. So it's a flip-flop that has an advantage of a simpler wiring than JK flip-flop. Okay, this is just a description, but I bet you know more than this basic description. So JK flip-flop is like the most versatile kind, okay, because it does not have this invalid state. Its SR flip-flop has an invalid state, okay, and the last flip-flop was a toggle flip-flop. This toggle flip-flop was actually derived from JK. So if you see a pattern over here, from JK flip-flop, you can derive a toggle flip-flop. From SR flip-flop, you can derive this D flip-flop, right? Just by connecting the input, right? So for SR flip-flop and JK flip-flop, they are kind of similar, but JK flip-flop overcomes the limitation of the SR flip-flop. The SR flip-flop, we have this invalid state. Invalid state when you have 2 of this to be 1s, you have invalid state. But in JK flip-flop, you can put this, and this makes your flip-flop to toggle. Okay, so those are the differences between all these types of flip-flop. All right, and this will be my last slide for today. Oh, too early. It's 8:30. Okay, so these are the differences between latches and flip-flops. So latches are, again, it's level triggered. So it depends on the enable. Your enable is high, your enable is low. And this flip-flops, they are edge triggered. So it functions when your clock is at the vertical line. It can be rising edge or it can be falling edge. So these are all the small differences that you can see. It's a synchronous device, flip-flop is a synchronous device. This 2 terms you would see in the next chapter. We'll talk about more about what this 2 means. Latches doesn't contain clock signal. Yes, it has enable, and flip-flop contains a clock signal. So you use the clock signal in flip-flops. Latches, it will change state as long as it is enabled. And flip-flop, it will change state only during given a clock cycle, right? So that's the difference. Latches consume less power. Of course, flip-flop consumes more power. Latches are faster and flip-flops are slower, as we can see over there in our timing diagram, right? So flip-flop, so latches actually react faster compared to flip-flop. All right, and we have D latch, T latch example. These are also example D flip-flop, T flip-flop. All right, I also attached this YouTube video over here. I really hope that you guys can go and watch this YouTube video, because this YouTube video is going to cover into much more detail of what I cannot cover in class. These are additional materials, not compulsory, but I highly recommend that you watch it, because I think that will help you gain the most from this class. Okay, so this will be my last slide of the class. Before we end the class, I would like to show you something. All right, so if you go to logic.ly and you go to demo, all right, so we can construct over here SR flip-flops. So if you go to the left, you have SR flip-flop, you have D flip-flop, and you have T flip-flop, and you have JK flip-flop. Okay, so you can construct all this flip-flop, and you can actually have fun constructing them. Let me show you a couple of tricks, then we will end our class today. Okay, let's delete this. This is an example of a SR flip-flop. I constructed this just now just before our class began. Okay, so SR flip-flop, in this very simple SR flip-flop, you have these two inputs and you have one output, and I connected the output to a bulb or a LED so that you can see what is the difference. So in the SR flip-flop, what happens if you have 0, 0 at the input? So 0, 0 means your flip-flop is in a no change mode, right? So no change mode. And over here, you have a clock signal. So whenever you have a clock signal, it turns blue over here, which means the flip-flop is triggered. Okay, so what happens currently is that the flip-flop is triggered, but your output is in it doesn't change. Why? Because the flip-flop is in a no change mode. Okay, get it? Right, so it triggers, but then the flip-flop is in the no change mode, so the output does not change. So let me change something. So I'm going to make this R into a high over here, and what's going to happen is that it's going to put your flip-flop in a reset mode. So reset mode means that your output is going to be turned into a 0, right? So let's just take a look, then turn it high. Okay, so what happens at the output? So whenever you put it into a reset mode, and then I hope you saw that just now, you put it into reset mode, and then the clock triggers, and then the output changes like that. Okay, so what happens if you put I'm going to change it into a set mode. I'm going to put this into 1, and over here I'm going to put this into 0. So you can already predict what's going to happen. So this is going to put your flip-flop into a set mode, and that will make your output to be 1. Let's just take a look. All right, take a look at that. Okay, it changes, and then okay, so I put this, gonna make it the output to be 0. Okay, so what happens if I put this? Okay, 0, 0 means it's gonna be in no change state, no change mode. So no change mode means it's gonna just preserve whatever output that you have. It's just gonna fix it right there. Okay, this is the basic of how SR flip-flop works. I really hope that you guys can just play around with this. So what other flip-flops you have? You have gates, you have yeah. Okay, so I guess you can play around with this flip-flop over here. Okay, so you have this D. All right, so for this D flip-flop, okay, take note that this D flip-flop, you have these two additional input, right? You have PRE. PRE stands for preset, and CLR stands for clear. So I want you guys to explore what this means. If you're in the lab, I think you guys also came across this preset and clear. Okay, so how do you explore this? It's easy. Just connect it to the input and see what happens, right? You can just connect this here, and you can connect this to the light bulb, and you can see what happens if you put it. Okay, you can see what is the difference between preset and what's the difference between clear. So I would like you guys to explore this, right? So by the end of today's class, I hope you guys already understood the difference. And there's T flip-flops, there is JK flip-flops as well. So as the assignment today, this will be the assignment for this chapter, right? Chapter 7. And I want you guys to reproduce the characteristic table of all of this flip-flop in logic.ly. Okay, So you can refer to this characteristic table. For example, like over here, we have a characteristic table of JK flip-flop. So you can reproduce every single line and make it into a video and submit that as your assignment for this chapter. Okay, so you can start your JK flip-flop with 0, 0, and then your existing output is 0. And you can show me in a video, you can present it to me saying that, okay, right now you have 0, 0, and your current output is 0. It's just going to stay like this because it is a no change state. So you can present it as if you're teaching me how this JK flip-flop works. Okay, so you can do that for all the 4 flip-flops. Okay, so that is your assignment for chapter 7, and as usual, this assignment I will give you 1 week to complete. All right, any question before we end our class today? It's a short class, but I think hopefully it's useful. It's a useful one. Okay, so before we end our class today, again, this is your attendance. If you came in late, you can scan your attendance. All right, just one last word before we end our class today. So as you are noticing, as we are progressing from the beginning of the semester until right now, we are at the ending of the semester. So what I am trying to do right now as we are moving towards the end is that I'm giving you more and more freedom. I'm giving you more and more freedom. You can see that our classes and our assignments, there are more homework that you need to do. There are more research that you need to do. Okay, so this is what I intend the class to be. So what I don't want to do in this class is I want to give you everything and then you just take whatever I say. I don't want that to happen. Okay, so what I want you guys to learn in this class is that I will give you a little bit and you take that little bit and you learn a lot more. That is what I want you to do. So that's why in chapter 7, this is going to be a fairly independent it's a chapter where I give you like research homework like this. So you can take a flip-flop, you can experiment with it, you can build with it, and you can find out how is it different. This is what I want you guys to do because I think this is how we learn best. Okay, that's one. You learn best by experiment. And number two, we learn best by teaching others. So this is something that I realized when I began teaching this class, digital logic. In the beginning, when I started to teach, I thought that I already knew everything about digital logic. I already knew everything about syllabus, but the moment I began to teach, I realized that, oh my God, I really don't know a lot. Actually, there's a lot of things that I'm missing out because the reason I can realize this is because I teach. So that is why in this assignment also, I want you guys to teach. In your midterm also, I told you guys that please teach an audience because it is only when you start to teach, then you begin to understand the topic even more. Okay, so in this assignment, I really hope that you use this flip-flop example and you start to teach this flip-flop to. In the video, you can imagine that you're teaching it to me, or you can imagine that you're teaching it to your junior, someone who doesn't know a lot about flip-flops. Okay, so I bet that the moment you do that, that is the moment that you will learn the most. All right, so that is the approach going forward. This is chapter 7, and we only have one more chapter left, chapter 8. We will cover chapter 8 next week, and chapter 8 also will be a very independent chapter. I will give you a little bit of things, and I hope that you take that little bit of things and you can explore a lot more behind. That is the way I want this class to be. I don't want everything. It's like, you know, the fisherman and fish thing I talked to you about in the last class. I don't wish that you just take all the fish that I'm about to give you because after the semester ends, I can no longer give you the fish, right? So yeah, I want you to take my fishing rod instead. Learn, take what I have to offer, take my tools, take whatever I can teach you on how to learn. Take this fishing rod and you can learn how to fish yourself instead. That is what I hope this class, this digital logic class will turn out to be. All right, so that is a little bit more on learning how to learn. And if you guys, after this semester ends, if you I don't blame you if you forget everything that I teach you in class. You can forget everything, no problem. I have no issues with that. But the one thing I hope that you don't forget is this one, is learning how to learn. All right, so learn how to learn any topic because you can use this concept and you can apply it to any other field, and that will make you into a very that will make you into a person who has a lot of advantage over many people because not many people actually invest time to learn how to learn. All right, so that will be the end of our class today. That will be the end of this chapter today, and from next week onwards, I will cover chapter 8, maybe partly of chapter 8, and next week also I will give you a briefing on your final class project. So do attend next week's class because it's going to be an important briefing for your project. All right, so that is all for our class today. If you have any questions, feel free to stay back and I will answer your questions. If you do not have any, scan your attendance and take care and have a good weekend. All right. All right. See you guys again soon. Bye-bye.
Thank you, sir. Have a good weekend.
Yep, you too.
Thank you, sir.
Thank you, sir.
All right, you're welcome.